just kind of jump right into the motivation. I'm interested, as a lot of contemporary behavioral economists are, in understanding how we can operationalize complexity, which is a word that's loosely used in the behavioral sciences, often with not much sharp meaning behind it, how we can operationalize it and measure it and use it in the predictive task of doing social science. So we'll just start out with with a standard loose version of the computer science definition of complexity, which is roughly the resource burden or the cost on a computational device of implementing an algorithm. And from the perspective of the behavioral sciences, not totally clear immediately this is going to be very useful for thinking about human behavior until we realize that for humans, most decision making is preceded by some sort of rule following, whether it's conscious or not. Okay, so people, in order to make decisions, have to choose or default to the use of a procedure. In order to make inferences, they have to perform calculations. In order to comply with policy, they have to follow a rule. In order to interact strategically, they have to choose a strategy. In order to think about the future and respond to the future, they have to implement plans, and so on and so forth. And you put these examples together and you realize that a lot of human decision making is formally or informally algorithmic. The idea, and then so you could think of an operationalization of complexity in humans as the cost of the algorithmic structure of performing these types of rules. So the idea in this paper is, and in the kind of research agenda it's attached to, is to try to measure these cognitive subjective costs of performing algorithms directly and use this to understand what makes rules, what makes procedures, what makes algorithms complex for humans to implement. And the science fiction version of what you might be able to do if behavioral scientists were able to do a careful job of this is that we could eventually use these characterizations of the cost functions of algorithms to predictively rank decision tasks prospectively according to how complex they are, how costly it is for them to discover and implement optimal solutions to decision problems. And similarly, we can predict what suboptimal algorithms look like, what it means to use a heuristic, why a heuristic is a heuristic, what makes them less costly and therefore likely to be favored. And this allows us, or could allow us, to not only predict what types of tasks people are likely to fail to behave in as we expect them to, but also what types of behaviors are most likely to divert to instead. And this is something that could be tremendously useful in developing policy and building institutions. The way I'm going to do this in this experiment, again, this is a kind of first shot at this enterprise, is to implement a kind of strange experiment. And in normal behavioral experiments, we give people a task, and in that task, their job is to decide on an approach to the task and then implement that approach. So they're being implicitly asked to find an algorithm to solve the problem. In this experiment, in order to do this kind of direct measurement, I'm instead going to assign subjects an algorithm directly, and I'm going to ask them to implement it. Okay, so that kind of thinking led to me to this eccentric experiment in which I show subjects a series of events, one at a time. Each event is a randomly drawn letter. So in this example, 5 events in red have happened so far: F, H, H, F, and H. And after each letter appears, the subject's job is just to type a letter in response. So here the subject has typed in K, K, I, K in response to the sequence of events they're seeing. And the trick is that I give subjects a rule telling me how I want them to progressively make choices as a function of the sequence of events that have occurred so far. So in this example, I've asked the subject, I've given the subject the rule, choose K until you see H, after which switch to I, then after you see F, switch to K, then after you see another F, switch to I, then start over after you see H. And if the subjects properly follow this rule by typing the unique sequence of 20 letters in response to the 20 events I show them on the screen one at a time, I'm going to pay them some money, and otherwise I'll pay them nothing. Okay, so that's the implementation test. The key to the experiment is, after giving subjects 14 of these, and I'll talk about how I selected these rules in a second, I then elicit subjects' willingness to pay to not be forced to play the same rule again in the future in the experiment. So subjects can essentially bribe me to not have to do these annoying tasks of implementing these algorithms. And the way this works is, on the left side of the screen, I give subjects a computationally trivial algorithm, type N 20 times, and I will pay them $2 if they do that. They use this slider to tell me how much the rule shown on the right would have to pay them for them to be willing to be assigned that rule instead. And this is, I pay subjects in an incentive compatible way with the BDM mechanism to get an accurate description of what this willingness to pay is. This willingness to pay gives me a measure of how much money the subject is willing to leave on the table to be assigned this easy algorithm instead of this hard algorithm. And that means that this measures the cost the subject experiences or thinks they're going to experience from being assigned this algorithm. And the cost of an algorithm is as close as we can come to an empirical measure of complexity according to the definition I'm working with. Okay. Now, in the background, I designed these rules with a kind of primitive language for describing algorithms in the background, finite state machines or finite automata, which are sort of coarse mathematical descriptions of algorithms from computer science. So here's an example, I'm going to show you a bunch of diagrams of these finite automata. So let me explain how they work in case anybody doesn't remember. Imagine I give the subject a rule. So I do give subjects this rule: choose X until you see B, at which point switch to Y, start over if you see A. And you can model this problem using as few as 2 states. Each state has an instruction for the subject, for the computer. In this state, the subject is supposed to type X. In this state, they're supposed to type Y. There's a series of transitions between states, and each of those transitions is triggered by one of the events in the environment. So what this rule says is start out choosing X, continue choosing X until you see a B, then switch to this state, start choosing Y, continue doing that until you see an A, do the A, start over. And this is just the simplest automata model of this rule. This rule, of course, is isomorphic to the rule tit for tat, which is an important rule in game theory. It's a famous strategy for playing infinitely repeated prisoners' dilemmas. The kind of question I'm interested in this paper is this alternative rule, or rules like it, more complex than the rule I just described? Okay, so this is a rule that says choose X until you see A, after which switch to Y, then after you see B, switch to X, then after you see another B, switch to Y, then start over after you see A. And the simplest finite state machine representation looks like this. Okay, and the question is this more complex than this? It has more stuff in it. So the simplest algorithm has more components. Which, if any of these components, make it more complex in the sense that it makes it more costly to implement? That's the kind of question I'm interested in here. In the experiment, I designed 14 rules. I spent a lot of time designing these rules to systematically vary primitives of these very simple algorithmic descriptions in systematic ways. So I vary systematically the number of transitions in excess of the number of states and the number of states. And then so within each cell, I have different state transition combinations, and I'm going to be measuring the cost for each of these for each subject. And then in some of these cells, I have more than one algorithm. In these cases, I'm varying other things in order to test some other theoretical questions about the drivers of complexity costs. So for instance, I have a rule called 4S3T that means 4 states and 3 transitions in excess of the number of states. And I also have a rule called 4S3TA. This is just like 4S3T, but it's designed so that there is an absorbing state that causes the rule to end. And I can look at whether absorbing states are different, rules are different from transitory state rules. Okay, here are the types of questions I want to ask with the design. Are algorithms per se costly to perform? Are they significantly costly to perform? Second question is, do those costs differ meaningfully across algorithms? So do people really treat different algorithms as if they're costly in different ways? And trying to translate that, are different algorithms complex for people to different degrees? The third question, this is the big one, is there operationalizable structure to these costs? Can I predict the costs of a rule based on mathematical characteristics of its algorithmic structure? The fourth is, do people, and these, now we start getting into sort of deeper questions about how we might want to go out modeling these things. Do people represent these algorithms to themselves accurately when assessing costs? And then finally, I'm using an extremely coarse descriptive language for modeling these algorithms, finite state machines. Is this a sufficiently rich grammar or taxonomy for describing what makes one rule more costly than another? So I'll make these last two a little bit more concrete in a second. Okay, so I'll just start out jumping right into the data given our time constraints by answering these first two questions. Okay, so what I'm going to do is I'm going to show you all 275 subjects from my experiment. On the y-axis, I'm going to show the cost the subject revealed to me and their willingness to pay for performing the rule. And I'm going to draw a dot showing the average cost for every subject in the data set. I'm going to organize those according to the number of mistakes the subjects made when trying to perform these rules as I instructed them. Okay, so I'll organize these in bins of 0 mistake, 1 mistake, 2 mistake, 3 mistake, and 4 mistake. That's the number of mistakes over 300 keystrokes, about 300 keystrokes required to, 280 keystrokes required to implement all of the rules properly. And what you can see from this is that subjects make very few mistakes in these rules. These rules are not difficult for the subjects to implement. They're capable of implementing them. The median subject, the modal subject, makes no mistakes in all of those keystrokes. The median only makes 1 mistake, and very few subjects make more than that. Okay, so this is not intractably difficult, but it is extremely annoying. So subjects are willing to pay me a significant proportion of their earnings, task by task, to avoid the average rule. Okay, so what these dots are showing, I'm ordering these from lowest to highest. Again, each of these dots is a separate subject. And even subjects who make very few mistakes are very willing, on average, to pay me several dollars just to not implement one of these rules again in the future. Okay, so that answers the first question. On average, even these algorithms that are completely doable are very costly for subjects to implement. Okay, the next thing I want to show you is for every subject, I'm going to draw a line between that spans the simplest and most complex algorithm as measured by the subject's costs or revealed costs. Okay, so this is going to give you the range of willingnesses to pay that the subject submitted across the 14 rules. And what you should see here is that subjects make huge distinctions across rules. The simplest, for the median subject, the most complex rule is a subject is willing to pay an order of magnitude more for the most complex rule than for the least complex rule they're assigned. It's okay, so not only are subjects finding these rules very costly, these costs differ meaningfully across algorithms. Okay, and then we get to the big question: is there some operationalizable structure to these costs? Okay, so we designed these 14 rules with an old literature in economics in mind. I'll call this the automata literature. This is a literature in economic theory that started in the theory of repeated games. This is not at all an empirical literature. It's a purely theoretical literature. And what this literature does is it models repeated game strategies as finite state machines, and it makes some assumptions on what mathematical characteristics of those machines produce direct implementation costs. And the idea was to use these costs to make repeated game theory, which is notoriously non-predictive. It tends to produce support many equilibria, and the idea was to make these more predictive. This has been applied to classic problems in economic theory, like the repeated prisoner's dilemma, the existence of competitive equilibria in markets, and things that are closer to behavioral economics, like why satisficing is computationally cheaper than rational choice. Okay, so I'm going to use this as a sort of inspiration for starting this out, for starting out thinking about this. And the first thing, the first theory I'll assess is something the literature sometimes called S complexity or state complexity. This is a hypothesis that rules that at their simplest have to be described with more states or more complex, more costly to decision makers. A state here in a finite state machine is a kind of amalgamation of different computational acts, including instruction, information processing, and it's also the only way that these algorithms can represent memory. And so a higher state rule is one that requires more information processing and more memory. Okay, so here's an example of a state simple rule, low state complexity. This has only two states. This rule 2s2t. This rule 4s2t has the same number of transitions in excess of the number of states, but it inserts two states into the rule. By comparing people's willingness to pay to avoid this rule, and other rules in between, we can get an estimate of the average contribution to complexity, the average increase in cost that comes from adding a state to a rule. Okay, and what you can see here, I'm going to plot this with total transitions. This is the number of transitions in the rule plus the number of states. And on the y-axis, I have elicited costs. And what you can see is that when I increase the number of states without increasing the number of transitions or changing out any other key morphological features of the rule, I get an increase in complexity costs. And this is a statistically significant effect and is one of the largest effects in the data set. So indeed, rules that contain more states are predictably more costly for people. Okay, the other sort of big coarse visual feature of a finite state machine is the number of transitions. So we have a set of rules that are designed to test the idea of T complexity, which is another idea that was floated around in the literature. Transitions are descriptions of the amount of monitoring the environment that's required by the rule and the amount of variability of behavior in response to changes in the environment. This rule 4s2t contains two transitions in excess of the number of states. This rule 4s4t contains four transitions in excess of the number of states. And we can do basically the same thing. Here's the data I already showed you. And here are the rules that were designed to measure transition costs. And as you can see, every time you add transitions, you also add costs, statistically significant amount of complexity to the rule, but the effect of a transition is much smaller than the effect of a state. Okay, and so you can see you start getting a kind of cost function over algorithms as a function of their mathematical characteristics. Okay, so there's much more on what these operationalizable structures look like, but generally speaking, the answer in the paper, but generally speaking, the answer is yes. There's a lot of structure in these costs, a lot of predictability. And so this kind of opens up the possibility that, again, in some science fiction future, we could we could predict what is going to make one decision problem more complex based on an understanding of what kind of rules would be required to optimally solve the problem for humans. Okay, so now I'll ask a couple of kind of deeper questions in the time remaining. I'm going to have to breeze over these a little bit, but if you're interested, there's lots of detail on this in the paper. So one question is, do people represent these algorithms to themselves? When they look at an algorithm, do they represent their costs accurately to themselves? The easiest way to explain what this means is an assumption often made in the theoretical literature in economics that tries to take complexity seriously, is that if a subject is considering using, or an agent is considering using a rule, that they're going to economize on the structure of that rule computationally and use the simplest version of that rule possible. You can do something like testing this by having two rules that descriptively on the surface look identical. This is 4S4T. It has 4 states and 4 transitions in excess of the number of states. We also have this rule called reducible. Reducible also has 4 states and 4 transitions. But if the person thinks hard about this, they can realize the rule reducible is isomorphic to the rule reduced. That is, it contains states that aren't necessary in order to perform the same sets of actions over any sequence of events. Okay, so the subject could heuristically shrink the reducible rule into the rule reduced at no cost. And so if people efficiently reduce rules in this way, they should treat this rule reducible as if it is much simpler than this rule 4S4T. Okay, and this is the rule reducible. This is the rule that on the surface it looks identical to. This is the rule that it's actually equivalent to if the subject were to reduce it. And what you can see is that the subject treats this rule as if it's just as complex as the rule is 4S4T, which means they don't economize on the complexity and the structure of the rule when they think about what they're trying to implement. They don't efficiently process these rules at all. Okay, that's important for thinking about how we apply these types of things to model human behavior. Okay, last, so people do not represent these algorithms themselves accurately when assessing costs. Instead, they use surface level pieces of the description of the rule to assess complexity costs. Okay, the final question is, what I'm doing here is I'm giving subjects rules and I'm picking the easiest to work with, coarsest, simplest descriptive language for talking about the rule. The rule that's highest up on the Chomsky hierarchy, and we can ask questions about using rules that are more descriptive, that make more distinctions across rules, but that are more sort of complicated to work with, and ask if those do a better job of summarizing and taxonomizing people's complexity costs. Okay, so I'll call this the assumption implicit in this older theory literature that interfaces with finite state machines, finite state machine representation. This is the strong assumptions about how rules are differentiated and how we go about classifying costs. In a finite state machine, states represent, as I said, distinct ways information can be processed, behavioral predictions, and event memory of what's happened so far in the rule. These were memories completely described or encoded in the rule using states. So a finite state machine treats these 3 functions identically, and this is a way of describing the descriptive poverty of this very simple 2-ingredient way of describing the complexity of a rule. Okay, so to show where this kind of thing might break down, this rule called 4S4T and this rule that I call countable are identical under the lens of finite state machines. But the simplest way of describing this rule 4S4T to a subject is to say, choose X, then switch to Y after you see A, then switch to X after you see B. When you see a second B, switch to Y and start over if you see A. Whereas this rule countable says, choose X until you've seen B 3 times, and then switch to Y, start over when you see A, which seems intuitively much easier for a human to implement. It just involves counting. We can differentiate these 2 rules from one another If we go one step down on the Chomsky hierarchy to a more descriptive language, so those are called push-down automata. I'm not going to go into the details here, but a push-down automata is like a finite state machine, but it allows it puts memory into a separate object called a memory stack. It looks like this. You have to describe how things are read and written to the memory stack, but this will make two rules like countable and 4s for t look very different from one another. And the paper has details on this, but indeed the rule countable is treated as much less costly than the rule 4s for t. Okay, and this directly suggests that finite state machine representations miss something important about what drives complexity for humans. Okay, I'll just skip that. So there's a lot more detail on this in the paper. More generally, we can test whether formal languages for describing algorithms are rich enough to describe complexity costs. The results in the paper show that finite state machines are not rich enough. Push-down automata organize these costs better, and this probably isn't the last word. You can easily imagine that we end up finding distinctions between types of rules that suggest we should go to very rich ways of representing algorithms like Turing machines. Okay, so I have 2 minutes. So I'm just going to mention some tenuous connections to cognitive primitives. Procedural learning, when people perform a rule many times, even though they haven't learned any new facts, their costs go way down. So complexity costs drop in humans when they are practiced in using a rule. Episodic memory doesn't seem to have anything to do with the types of complexity costs I'm measuring. So I have a version of the experiment in which I show people the events and choices one at a time, and it basically makes no difference. So you get all the same results I just showed you. On the other hand, having to implement a rule in your head instead of implementing the rule one step at a time is significantly more complex and significantly more costly for humans. So if I show people all of the events and I just ask them to type the last choice that would happen if they were to follow the rule over the sequence of events, they don't make any more mistakes, but they hate it a lot more. It's far more costly. They're willing to pay a lot more to avoid this kind of thing. Okay, and then there's some follow-up experiments. I have a paper with James Banovitz that was just published last year that studies whether these types of costs matter in real decision making, but I will skip that. The answer is yes. Okay, so this is just a proof of concept for a much broader enterprise. We could judge decision problems not by the primitives of the decision problems, but by the algorithmic cost of making optimal choices in them. And we might be able to use this to predict what classes of heuristic alternatives are less costly and are likely to be selected instead of optimal choice rules. The idea is that someday we could use this kind of thing to build models of bounded rationality that are rooted in sort of empirically grounded measurements, characterizations of what makes one type of behavior more complex than another. We also use this to design rules, laws, organizational codes, bureaucracies that are easier to comply with and therefore more likely to work as intended. Okay, I'm out of time. Thank you.